Hello everyone, I am Meenakshi, student of BSc Chemistry Honours. Today I am going to prepare a video on the chapter of organic chemistry, that is alkenes, for visually impaired students. So let's start. Introduction. Unsaturated aliphatic hydrocarbons containing two hydrogen atoms less than the corresponding alkanes and which are characterized by the presence of a double bond in their molecule are called alkenes. They are also called olefins since the lower member of this class, like ethylene, form oily products on reaction with halogens such as chlorine and bromine. Their general formula is CnH2n, where N is 2, 3, 4, etc. Unsaturated hydrocarbon containing 2 and 3 double bond are also known. They are called alkadienes or alkatryienes respectively. The general formula of alkadienes is CnH2n-2, where N is 4, 5, 6, etc. And that of alkatryienes is CnH2n-4, where N is 6, 7, 8, etc. The term polyene used for unsaturated hydrocarbons containing several double bonds. Nomenclature of alkenes. Common system. In the common system, unsaturated hydrocarbon containing a double bond are called olefins. The name of an individual olefin is obtained by replacing the suffix "ene" from the name of corresponding alkane by "ylene", that is the common name. Alkane plus "ene" plus ylene, alkylene. In case of isomeric olefins, the position of double bond is indicated by Greek letters alpha, beta, gamma, delta, etc. The numbering being done from a direction which gives the lowest Greek alphabet to the carbon atom carrying the double bond. Sometimes prefixes such as iso are also used for the branched chain isomers. IUPAC system. In the IUPAC system, the unsaturated hydrocarbons containing a double bond are called alkenes. The name of individual alkene is derived by replacing the suffix "ene" of corresponding alkene by "ene", that is IUPAC names alkene. The following rules are generally followed while naming alkenes according to IUPAC system. The longest carbon chain containing the double bond is chosen as the parent alkene. The position of the double bond and the substituent, if any, are indicated by Arabic numerals 1, 2, 3, etc. Numbering being done from that side which gives the lowest number to the double bond. If while numbering the chain, the double bond receives the same number from either side, the carbon chain is numbered in such a way that the substituent gets the lowest number. The position of the substituent separated by hyphen is either prefixed to the name of alkene or placed before the suffix "ene". The name of the substituent on the carbon chain is prefixed preceded by its position to the name of parent alkene. A hyphen separates the position and the name of substituent. If there are more than one substituent, each substituent preceded by its position is arranged alphabetical order before the name of parent alkene. In case of same substituent is repeated twice, thrice, 4 times, etc., the prefix di, tri, tetra, etc. are attached to the name of substituent. While deciding the alphabetical order of the various substituents, the prefix di, tri, tetra, etc. are not considered. The common and IUPAC names of some of important members of this class, like CH2 double bond CH2, common name is ethylene and IUPAC name is ethene. CH3 CH double bond CH2, common name is propylene and IUPAC name is propene. Alkenyl group. The monovalent alkyl group obtained by removing a hydrogen atom from ethylene is called vinyl group or ethenyl group, and that derived from propylene by removing a hydrogen atom from the double bond carbon atoms is called propenyl group. If, however, a hydrogen atom is removed from the methyl group of propylene, the alkylene group is called allyl group. CH2 double bond CH, vinyl group, CH3 CH double bond CH, 1 propenyl. Methods of formation of alkene. Alkenes can be prepared in the laboratory by the following general methods. Dehydrohalogenation of alkyl halide. Removal of the elements of hydrogen halides from the adjacent carbon atoms of an alkyl halide is called dehydrohalogenation. Dehydrohalogenation of an alkyl halide gives fair to good yields of alkene and is generally carried out by heating an alkyl halide with a strong base such as sodium ethoxide or a concentrated alcoholic solution of potassium hydroxide. For example, ethyl bromine reacts with alcoholic KOH, gives ethylene plus KBr plus H2O. Mechanism. Dehydrohalogenation of alkyl halide is an example of elimination reaction. Elimination reactions occur by a number of different mechanisms, but we shall discuss here only two of them, E2 and E1. Dehydrohalogenation of a majority of primary alkyl halides occurs by E2 mechanism. Kinetic study of these reactions reveal that the reaction follow the second order kinetics, that is, the rate of reaction is proportional to the concentration of both alkyl halide and base. This means that E2 reaction is a one-step process and occurs through a transition state. As the hydroxide ion begins to abstract the proton from beta carbon atom, the carbon-hydrogen sigma bond begins to break and a new carbon-carbon pi bond begins to form, and the leaving group from the alpha carbon begin to depart, taking with it the electron pair from the carbon-halogen sigma bond. Thus, the dehydrohalogenation of alkyl halides occur by a concerted mechanism in which the carbon-hydrogen and carbon-halogen sigma bonds are broken and carbon-carbon pi bond is formed approximately at the same time. An important aspect of elimination reaction is that they are always accompanied by the substitution reactions as well. Thus, in the above reaction, along with ethylene, some ethyl alcohol is also formed. Stereochemistry. It has been observed that E2 elimination reactions are much more facile when two departing groups H and X are trans with respect to each other rather than cis. For example, trans 2-bromo 2-butene forms dimethyl acetylene more readily than the cis isomer. E1 elimination unimolecular reaction. Many secondary and tertiary alkyl halides undergo elimination reaction when heating in an ionized solvent. For example, tert-butyl bromide, when heated in alcohol, undergo dehydrobromination to form isobutylene. Tert-butyl bromide reacts with C2H5OH, gives isobutylene plus HBr. Studies on this reaction have indicated that it follows the first order kinetics. The rate of the reaction is proportional to the concentration of alkyl halide only. This rate law suggests that only alkyl halide is taking part in the rate determining step of the reaction. This means that the E1 reaction is a two-step process involving the immediate formation of carbocations. The first step involving the ionization of alkyl halide to form a carbocation. This step is slow and hence the rate determining step of the reaction. The second step involves the rapid loss of a proton from an alkene. This step is fast and hence does not affect the rate of reaction. It may be noted here that in case of even reaction depend upon the stability of carbocation. Further, unlike E2 reaction, even reaction have no stereochemical preferences since they involve the carbocation which are planar chemical species. However, like E2 reaction, even reactions are also accompanied by the substitution as N1 reaction. Regiochemistry or the orientation of even and E2 reaction. Stage of rule. An interesting feature of an elimination reaction is that a mixture of isomeric alkenes is invariably formed if the structure of alkyl halide is such that the double bond can be formed in two possible directions. An interesting feature of elimination reaction is that a mixture of isomeric alkenes is invariably formed if the structure of alkyl halide is such that the double bond can be formed in two possible directions. Out of these two isomeric alkenes, the alkenes which is more stable is formed in greater amount. But we know the greater the number of substituent across the double bonded carbon, more stable is the alkene. Thus, in almost all the E1 and most of the E2 reaction, the more highly substituted alkene predominates. This generalization is called stage of rule. For example, dehydrobromination of 2-bromobutane gives a more stable 2-butane in 80% yield and the less stable 1-butene in 20% yield. Further, the more highly substituted alkene can often exist as a cis and trans isomer. Due to the greater stability of trans over the corresponding cis isomer, trans alkenes are predominant products of E1 and E2 reactions. Dehydrohalogenation of vicinal dihalides. The dihalogen compounds in which two halogen atoms are attached to the adjacent carbon atoms are called vicinal dihalides. These, when heated with zinc dust, lose a molecule of halogen as zinc halide to form alkene. This reaction is known as dehalogenation. Thus, 1,2-dibromoethane reacts with Zn in presence of alcohol gives ethane plus ZnPr2. This reaction is not a useful method for preparation of alkene since the dihalides needed for the purpose are themselves prepared from alkenes by the addition of halogen. However, this method is very suitable for purification of compounds containing double bond and for the protection of carbon-carbon double bond in the chemical reaction. Dehydration of alcohol. By dehydration, we means the removal of a molecule of water. Alcohol on dehydration gives alkene. Dehydration is carried out by heating a suitable alcohol with protonic acid such as H2SO4, H3PO4, Lewis acid such as anhydrous zinc chloride, and alumina can be used. The actual temperature and the strength of acid, however, depends upon the nature of alcohol used. For example, primary alcohols such as ethyl alcohol and propyl alcohol, etc. undergo dehydration when heated with 95% H2SO4 at 433 to 443 Kelvin to give ethylene and propylene respectively. On the other hand, dehydration of secondary and tertiary alcohol occur with dilute H2SO4 at lower temperatures. For example, isopropyl alcohol, a secondary alcohol, reacts with 60% H2SO4 at 413 Kelvin gives propylene. Thus, the order of dehydration of alcohol always follow a sequence tertiary, secondary, primary. In industry, the dehydration of alcohol is carried out by passing the vapors of an alcohol over heated alumina. Mechanism. Dehydration of alcohol is another example of an even reaction. This mechanism involves three steps. An alcohol being a Lewis acid accepts a proton from the strong acid to form a molecule of protonated alcohol, oxonium ion. The presence of positive charge on an oxygen atom in oxonium ion weakens the CO bond, thus it readily eliminates a water molecule from the carbocation. The carbocation formed in the second step, being reactive chemical species, eliminates a proton from a beta carbon atom to form alkene. The loss of proton may be assisted by the base, that is H2SO4 negative ion, or the another molecule of alcohol. This whole process is reversible. In order to shift the equilibrium towards right, strong acid and high temperature are used when the volatile alkenes escape from the reaction mixture. Evidence in the support of above mechanism. Relative ease of dehydration of alcohols. Step 2 in the above mechanism involving the formation of carbocation is a rate determining step of the reaction. Evidently, greater the stability of the carbocation formed, the more easily it would be formed and hence more readily the alcohol will be dehydrated. Now, since the order of the stability of carbocation follows the sequence tertiary, secondary, primary, hence the ease of dehydration also follows the same sequence tertiary, secondary, primary alcohol. Formation of unexpected products. It has been observed that certain alcohols on dehydration produces such alkenes in predominates amount in which the position of double bond is not that expected from the structure of original alcohol. The formation of such unexpected products can be easily explained on the basis of carbocation intermediates. We know the carbocation always tends to rearrange to more stable carbocations if structure permits, either by 1,2-hydride or by 1,2-methyl shift. Thus, in the dehydration of alcohols, if the initially formed carbocation is primary or secondary, and if the structure permits, it would always tend to rearrange to the more stable secondary or tertiary carbocation before losing a proton. Rearrangement by hydride ion shift. During the dehydration of N-butyl alcohol, the initially formed carbocation is N-butyl carbocation, which is primary. It undergo 1,2-hydride shift to form secondary butyl carbocation in before losing proton. Rearrangement by 1,2-alkyl shift. Acid catalyzed dehydration of 3,3-dimethyl butane 2-ol gives the rearranged product 2,3-dimethyl butene as the major product, while the expected product, that is 3,3-dimethyl butene, obtained in minor product. The formation of major product may be explained by the rearrangement of initially formed carbocation, which is secondary to the more stable tertiary carbocation, by 1,2-methyl shift as shown. Regiochemistry or orientation in the dehydration. When isomeric alkenes are possible during dehydration of alcohol, the more stable, the more highly substituted alkene is always the predominant product. For example, 2-butanol reacts with H2SO4 in presence of heat, gives 2-butene major and 1-butene minor. The formation of these products can be easily explained in the terms of arrangement of initially formed less stable carbocation to the more stable carbocation, followed by loss of proton. Hofmann elimination. Besides dehydrohalogenation of alkyl halides, alkene can also be prepared by the pyrolysis of quaternary ammonium hydroxide. A quaternary ammonium hydroxide gives alkene CH3 thrice N plus H2. This reaction is called Hofmann elimination reaction and forms the basis of Hofmann's method of elimination of nitrogen from an organic base by exhaustive methylation. Quaternary ammonium hydroxide needed for this purpose are usually prepared from the corresponding quaternary ammonium halides by treating them in aqueous solution of silver oxide or anion exchange resin. Mechanism. Hofmann elimination reaction is an E2 reaction in which the hydroxide ion removes a proton and positively charged nitrogen act as a leaving group. Physical properties of alkene. Physical state and smell. The first three members of the family, ethene, propene, butenes, are colorless gases. The next 11 members are liquids, while the higher ones are solid, except ethene, which has a pleasant smell. All other alkenes are odorless. Melting point. The melting point of alkenes do not show a regular gradation. However, the melting point of alkenes are higher than those of alkenes. This is due to the reason that the pi electrons of double bond are more polarizable than sigma electrons of single bond. As a result, intermolecular forces of attraction are stronger in alkenes than in alkanes, and hence alkenes have a higher melting point than that of corresponding alkenes. Amongst isomeric alkenes, trans alkenes have higher melting point than corresponding cis alkene due to the reason that the molecules of trans alkene, being symmetrical, pack more closely in the crystal lattice than the molecules of cis alkene, which are less symmetrical. As the result, greater amount of energy is required to break the crystal lattice of trans alkene than the corresponding cis alkene, and hence the trans alkene have a higher melting point than that of corresponding cis isomer. Dipole moment. Symmetrical trans alkenes are non-polar and hence have zero dipole moment. Since the dipole moments of individual groups, being equal and opposite, exactly cancel out each other, unsymmetrical trans alkenes, however, have a small but finite dipole moment. The reason being that Although the two dipole opposite each other, yet they do not exactly cancel out each other since they are unequal. Both symmetrical and unsymmetrical trans alkenes are polar molecules and hence have finite dipole moments. The reason being that in this case, two dipole moments are inclined to each other at the angle of about 60 and hence have a finite dipole moment. For example, cis 2 butene have a dipole moment of 0.25 d dipole and cis pent 2 ene have a dipole moment that is smaller than 0. Similarly, unsymmetrical terminal alkenes such as propene and but1-ene have a finite dipole moment since the polarity due to the alkyl group is not cancelled by corresponding polarity in the opposite direction. Boiling point. The boiling point of alkenes, like alkanes, show regular gradation with increase in number of carbon atom. Except for the first few members, the boiling point increases by about 20 to 30 for addition of each carbon. The branched tail alkenes, however, have lower boiling points than the corresponding straight chain alkenes. Amongst the alkenes which show geometrical isomerism, cis alkenes have a higher boiling point than the trans isomers. This is due to the reason that the cis alkenes, being polar, have a strong dipole-dipole interaction, while trans alkenes, being non-polar or weakly polar, have weak induced dipole interaction. Solubility. Alkenes, like alkanes, being either non-polar or weakly polar molecules, are practically insoluble in water and other polar solvents, but quite soluble in non-polar solvents such as benzene, CCl4, petroleum ether. Density. The density of alkenes, like those of alkene, increases with increase in molecular mass till they have a limiting value of 0.839 gram per centimeter cube. Thus, all the alkenes are lighter than water. Hydrogenation and the relative stability of alkenes. Alkenes add on hydrogen in presence of finely divided metals such as platinum, palladium, Raney, nickel to form alkenes. This reaction is called hydrogenation and used to determine the number of carbon-carbon double bond or triple bonds in an organic molecule. For each double bond, 1 mole of H2 22.4 liter at NTP is absorbed. Mechanism. Hydrogenation of alkenes and alkynes is a cis addition process. Catalyst H2S hydrogen adsorbed on the surface of catalyst. Complex of alkene with catalyst. Alkene product regenerate catalyst. Insertion of hydrogen into carbon-carbon double bond. Here, first H2 get adsorbed on the H atom as H atom on the surface of a catalyst using its vacant d orbitals. This is followed by adsorption of unsaturated compound through its pi electron. Thereafter, transfer of adsorbed H atom occurs on the same face of unsaturated compound, giving cis addition product. The reduced product finally gets deabsorbed from the surface of catalyst, leaving room for fresh adsorption of H2 and unsaturated compound. Heat of hydrogenation. Hydrogenation is an exothermic reaction and the amount of heat evolved when 1 mole of alkene is hydrogenated is called heat of hydrogenation. But1-ene, cis-but2-ene, trans-but2-ene, all on hydrogenation give the same alkene and butene but evolves different heat of hydrogenation. This means that these alkenes must have different inherent energies and hence different stabilities. An alkene which has a lower heat of hydrogenation must have less inherent energy and hence will be more stable than its isomer which have higher heats of hydrogenation. Thus, the heat of hydrogenation of an alkene is a measure of its stability. The lower the heat of hydrogenation of alkene, more stable it is. The following conclusion can be drawn. An unsubstituted alkene such as ethene has the highest heat of hydrogenation. Greater the number of alkyl groups attached to doubly bonded carbon atom, more stable is the alkene. In general, Alkenes have the following decreasing order of stability. Out of geometric isomers, trans isomer is slightly more stable than the corresponding cis isomer. Explanation for the relative stability of alkenes. The relative stabilities of different alkenes can be explained on the basis of concept of hyperconjugation as discussed in Unit 1. Consider, for example, the following alkenes: 2,3-dimethylbutadiene, 2-methylbutadiene. 2,3-dimethylbutadiene have 12 alpha hydrogen and 2-methylbutadiene have 9 alpha hydrogen. Which have more alpha hydrogen have more heat of hydrogenation and that will be more stable. Alkenes 1, 2, 3, 4, 5 have 12, 9, 6, 3 and none alpha hydrogen respectively, hence equal number of hyperconjugating structure and can be written, since greater the number of hyperconjugating structure, more stable is the alkene. Chemical reactions.